So let's use what we've learned in the calculus of variations in order to derive the equations of motion of a double pendulum. So I've got the double pendulum drawn out here. We have a y-axis and we have an x-axis. So there's one pendulum here you can see given by L1 with mass m1, and the second pendulum is attached to the end and it's got a length L2 and a mass m2. Now the fulcrum for this pendulum here is defined at the origin. So that means that we come along this distance in x, it's a positive distance, but when we're coming down this distance here, it's going to be a minus y distance. Now we define the angle θ1 as the angle that the pendulum makes with the vertical axis. And you can see that we've got an angle θ2, so this is the angle that the pendulum 2 makes with the vertical axis. So we can call this pendulum L1 the inner pendulum, and we can call the pendulum L2 the outer pendulum. So now what we're interested in doing is finding the positions and the velocities of the points, first of all of M1 and M2. Now we're going to do that by resolving all of the distances. So we're going to look at it in terms of a distance x1 and y1 for pendulum L1, and it's going to be a distance x2 and y2 for pendulum L2. So let's look at these distances in terms of the angles θ1 and θ2. So we can see here that θ1, x1 is going to be the opposite of this angle, so we have the opposite over the hypotenuse, which is going to give us the sine. So we can say that x1 is equal to L1 sine θ1. So make sure you understand how I got that. It's just basic trigonometry. And we can see here that the distance x2, well, it's going to be the x1 plus this distance here. But again, you can see this distance here is going to be the opposite of the angle. So it's opposite over hypotenuse again, which is going to give us the sine. So we can see here that this distance here is going to be L2 sine θ2. So the x2 is going to be the x1 plus L2 sine θ2. Now we can do the same for the y coordinates. We have the y1, so this is the adjacent of the angle, so it's adjacent over hypotenuse, which is going to give us the cosine. So this is going to, length is going to be given by L1 cos θ1, but remember it's going to be a minus value because it's defined the origin at this point here, so we're coming down to the point. And then we can say that the value y2 is going to be the value y1, and we've got to add on the distance here, this small distance here. So this distance here is the adjacent, and the distance here is the hypotenuse, so it's adjacent over hypotenuse, which is going to be the cosine. So the small length here is going to be the L2 cos θ2, and it's minus because it's in the minus direction. So the y2 is equal to y1 minus L2 cos θ2. So what we have here are four equations of position. They relate the x1, y1, x2 and y2 to the angle theta. So these here are functions of the angle theta. But we're wanting to find the velocity of these. So what we're going to have to do is differentiate them. But of course the velocity is with respect to time. So we can see here that, for example, x1 is going to be a function of θ1. But θ1 in turn is going to be a function of time. So therefore whenever we differentiate these, we're going to have to use the chain rule. In order to find dx by dt, we're going to have to find dx by d theta times d theta by dt. So x is a function of theta and theta is a function of t. Now the same thing happens in the y direction. We're going to have dy by dt is equal to dy by d theta times d theta by dt. So all we have to do now is go ahead and differentiate these in order to get the velocities. So I'm going to use the dot notation. So the dot means with differentiated with respect to time. So if I differentiate the first one here, we can see we're going to have sine differentiates to cosine, so we're left with L1 cos theta 1. So this is the first part here, and we've got to do our d theta by dt, which is our theta 1 dot. And we can see that our x2 is x2 dot. We're going to have to differentiate this here. So we've already differentiated the first one, that's the same as above. And we're going to differentiate the second, and again, sine will give us cosine, so that's going to give us L2 cos theta 2 times theta 2 dot, okay, which is the last part of it here. Now we've got to do the same for our y1 and y2. So when we differentiate cos, we get minus sine, the minuses cancel out, and that's just left with L1 sine theta 1, and we've got the rest of the chain rule, which is going to be our theta 1 dot. And again, our y2 is equal to our y1, and we've got to add on the second part of it. So y2 is going to equal the y1, which is the same as above. Okay, we've already differentiated it, and when we differentiate the second part here, we differentiate cosine, we get minus sine, the minuses cancel out, and we get our L2 sine theta 2, and then from the chain rule we've got to differentiate, get our theta 2 dot. So these four equations here are the velocity equations, and we're going to use these in the next video in order to continue deriving the equations of motion of the double pendulum. So thank you for listening. I'll get you in the next video. Goodbye.